Welcome back. So this is our fifth lecture on the MATLAB, computational methods and MATLAB, right? So this is our fifth lecture. So in fourth lecture we have solved some problem we have solved some demonstration problems. We have also solved a problem on Hempel pendulum in the first lecture. So today actually we will be discussing about one toolbox. As I said that MATLAB had a structure, and in the structure LMAT. LMAT is one of the directories where you will have elementary matrix operations. So we have been covering each of the toolboxes. As you can see the screen, if you see the look at the screen, so this is the elementary matrix directory where you have got different functions. For example, to create elementary matrices like zeros, ones, I means identity, replicating matrices, random number generations, uniformly distributed random numbers and normally distributed random numbers, and linearly spaced vectors. As you can see, linearly spaced vector, logarithmically spaced vector, frequency spacing. This is important when you go for frequency response. We will be discussing this when you discuss signal processing and control system toolbox. Mesh grid, accumulating arrays from vectors, then basic operation on the arrays, that is finding out the size of the array, length of the array, length means the maximum dimension, then number of dimensions, because the arrays maybe have multiple dimensions, not necessarily single dimension. It can be two-dimensional array, three-dimensional array, then number of elements, displaying the matrix, whether testing the array whether it is empty or not, testing the array if two arrays are equal or not. Then we have to find out if the arrays are numerically equal or not. Okay. Matrix manipulation, then concatenating the arrays, that means joining two arrays, changing the shape of the arrays, diagonal matrices and diagonals of a matrix, block diagonal, extracting the lower triangular part, extracting the upper triangular part, then flipping the matrix left right direction. Just if the matrix is, just you flip it left right, just like flipping an image, then flipping up and down, then flip the matrix along specified dimension, then rotating the matrix, then colon. So this is a very important character which is necessary for indexing a particular matrix and filling a particular matrix. Then finding indices of non-zero elements, last index, then subscript to index and index to subscript. We will be discussing about this when you discuss about structures. Then n grid, permute, I permute, shift dimension, circular shift, squeeze, is scalar and is vector. So if it is just a logical operator, whether if it is a scalar it will be true, if it is a vector it will be true. Then special variables like answer, epsilon, real max, real mean, pi, I, infinite, not a number, true. Then logical operators like is none, is infinity, is finite. Then again imaginary answer, then y, which will give you some funny answers. Then these specialized matrices, if you operate with these functions, you will able to generate specialized matrices like matrices of companion form, Higham test matrices, Hadamard matrix, Hankel, Hilbert matrix, inverse Hilbert matrix, Maggi square, Pascal matrix, classic symmetric eigenvalue test problem, that is Rosser's matrix, Toeplitz matrix, Van der Monde matrix, Wicklies matrix, and many more. So gallery will give you lot of matrices. If you go to gallery, it will give you lot of different kinds of matrices like Cauchy, Cheby band, Chow, circulants, Clement, counter, Dor matrix, Fielder, Forsyth, Frank matrices. So there are different kinds of matrices which you can get it from gallery. So out of them, as I said every class, that we have to find out what are the most used functions, and as far as you are concerned, those who are beginners, even for sufficiently advanced users, I will just mark few of them. So please look at my look at my note, you can see actually I have written few things. One is that elementary LMAT directory. So today we are going to discuss about elementary LMAT directory, about different functions. Then we shall discuss about two interesting problems, because you will be getting bored by discussing only functions. So I shall tell you how to solve a differential equation. Then also I shall tell you how to fit a curve. So these are some of the things which will be very useful for you along with learning the elementary matrix functions. So I am writing down, you can see in the important functions. So I am writing important functions in LMAT. So what is this? So please remember that LMAT is one of the directories under MATLAB which will store these functions. So now I shall write zeros. This is function number 1, which is important. Then ones, then I gives you the identity matrix, then rand, then rand n, then 6 lean space, then log space, then 8 mesh grid, and 9 column. So let me discuss these functions right now, which are important. Other things you can learn by help. You cannot learn everything by this lecture. So I will be discussing in the elementary matrices. So these functions first, then I shall move to basic array information. So let me discuss these functions, these matrices. I will give you one example in each of them. So these are very important and very much used. Frequency space, accumulation of array, and other things you may learn later on by just using help. You don't have to learn right now. Okay. So let me give examples of each of them. So zeros, for example. So if you want to have a matrix of zeros, let us say I want to have a matrix of 3 by 3 matrix of zeros. So what I can do is just I will write zeros 3. So you will get a 3 by 3 matrix of zeros. Suppose I want to have a 3 by 2 matrix of zeros, then I can just write zeros 3 by 2, right? Similarly, ones. Similarly, if I want to have a matrix of ones like 4 by 3, I can have a matrix of ones. Suppose I want to have a identity matrix, R is equal to, I want to have an identity matrix which is 4 by 4, I will just write I4. Suppose I want to write like this, I3, 4. So you can see what kind of identity matrix you will get. You will get the one of the diagonals. You can see here these diagonal, one of the principal diagonals will become 1, rest will be 0. So this is not a perfect identity matrix as you can see, but the diagonal, one of the lower diagonals is 0, because this is not a square matrix. Similarly, random matrix. So there are two random numbers, RAND and RANDN. As you can see here, this is RAND and RANDN. So RAND gives you uniformly distributed random numbers. So if you just write RAND, it will give you one uniformly just one random number. So unknown number which will be assigned to a variable answer, ANS. As I said earlier, that ANS is a variable which is inbuilt to the system. So if I want to find out a random vector, let us say V, which is having a dimension, let us say 1000. So I have this random vector V. So how to know whether this vector is random or not? So make a bar chart of this V. You can see whether they are random or not, whether they are uniformly distributed or not. You can see that. So it is taking little time. So in the meantime, I shall tell you what is rand_n. So rand_n is actually a normally distributed random number. It is a normally distributed random number. Whenever you say normally distributed random number, that is rand_n. If you say something is normally distributed, let me do plot V, that will be better. So when I see normally distributed random number, it is whatever random number will come out, that is having normal distribution. How the normal distribution look like? That means the probability distribution means the probability distribution. The normal distribution is generally bell shaped like this. So if you plot the probability of that particular number x, and x is the number, then what is the probability that the number will occur? Then it will have some kind of bell shaped distribution. So with having a mean, let us say x bar, and with a standard deviation sigma, right? But rand is uniformly distributed random number between 0 to 1, and randn will have always mean x bar is equal to 0 and a standard deviation will be 1. So now we can look at the screen. In this screen which you have plotted is a random vector of dimension 1000. So there are 1000 numbers which are plotted. If I plot little differently, as you can see, I will plot little differently. So I have plotted little differently. I have plotted, you can see the distribution. So this is the minimum is 0 and the maximum axis is 1. You can see here the minimum is 0 and maximum is 1. So if it is so, and there are 1000 numbers as you can see, and all these 1000 numbers as you can see are uniformly distributed, almost uniformly distributed between 0 and 1. This can be also verified by plotting histogram. For example, if I plot the histogram of P, that means the whole range of P, it is from 0 to 1, I will divide into, let us say, 20 different sectors, 20 different intervals, and in each interval I will find out how many numbers are there. So if I do so, I will get a histogram. So as you can see, this is your histogram. So this histogram tells you that these are the intervals 0 to 0.5, 0.05 to 0.1, 0.1 to 0.15, like that. So there are 20 intervals, and in each interval how many numbers are there? It is almost uniform. So you have proved that the random numbers which I have generated is distributed between 0 to 1 and it is uniformly distributed. So let us again generate some random number by using randn. For example, I want to generate a random number y which is equal to randn, which is having same, let us say 1000 by 1. So you can also generate a random matrix. So instead of 1000 by 1, you can make it 10 by 20. That will give a random matrix of random number. So now if I plot this y, let me plot this y. So if I plot this y, what do I see? So I can see that, so this is y which is varying. You can see the y, the maximum and minimum of y, because it is normally distributed. As I said, that the minimum and maximum bound is not fixed, unlike your uniformly distributed random numbers which is fixed between 0 and 1. Here actually the minimum bound is minus infinity, the maximum bound is plus infinity, but they will be distributed around 0 mean, as you can see, with the standard deviation unity. So if you want to plot differently, as I said, let me plot differently. You can see I have plotted it differently. So here you can see the numbers are closer towards 0. More numbers are concentrated towards 0 and less numbers are going off. That means they are normally distributed. Maximum numbers will lie around 0 axis. So let me find out the standard deviation of x. So if I find out the standard deviation of x, it is very close to, you will find unity. Sorry, standard deviation of y. I am sorry, standard deviation of y 0.9435, because you have taken only 1000. So if you find the mean of y, you will find this will be very small. That is, it is close to 0. You can see it is close to 0. So if you, same thing, if you do the histogram of y, see what is happening. If you plot the histogram, see, beautiful, it is showing almost a normal distribution, having 0 mean, and it is spreading both ways. It is bell shaped, right? So if you take more number of random numbers, you will find it is more close to normal distribution. So therefore you have proved that this is a random number. Now suppose I am interested to generate a random matrix. Let us say, let me clear all the variables again, start from fresh, clear all. So I'll make one random variable. Let me do a random variable x, which is equal to randn 5 by 7. What does it mean? That means I have a matrix of 5 cross a 7 dimension, having normally distributed random numbers with 0 mean and standard deviation 1. So that is how you generated the random number. Suppose somebody asks you, okay, now you generate a random number, whose mean is 10 and standard deviation is 5. How you are going to generate? So problem is generate a random number. You generate a random vector, let us say random vector with mean is equal to 5 and standard deviation is equal to, let us say, 3. So how would you do it? So it is very easy. So first of all, you generate the random number with standard deviation 3. So the same, use v is equal to rand n. So let us say 100 comma 1. I am generating 100 random numbers. What is the standard deviation of this? This is standard deviation is 1. So how can I increase the standard deviation? So what I can do is I can just multiply this with, let us say, 3. 3 is my standard deviation I need. Or let me make it 1000. 1000 cross 1, it will be easier. So v is having standard deviation 3. You can find out the standard deviation of v. See what is happening. It is close to 3. What is the mean of v? Mean of v is still 0. So you can see the mean of v is still 0. So how to change the mean? It is 0. Actually, it is very close, because be very small, because it is actually it is only 1000. So you are not getting it, but it is actually very small. So how to increase the mean? So just add. So v is equal to v plus 5. So that gives you mean 5. So mean of v will be now almost very close to 5, right? So standard deviation of v will be equal to 3, right? So if you plot the histogram of v, you can see what is happening. Taking little time. All right. So we have discussed about the random numbers. So it will come later. Let us not worry about it. So now I will discuss about linear spacing. What is linear spacing and what is logarithm spacing and what is mesh grid. So these three important functions I am going to discuss right now. So see, so this is your distribution of v. You can see this is having flatter because the standard deviation has increased. So this is flatter. So mean is around 5, right? So similarly, suppose somebody asks you to find out uniformly distributed random number between 0 to 10. How do you do it? So uniformly distributed random number between 0 to 10. What are you going to do? So you can generate a random number. First you clear. So you generate a random number by using rand, which will give you, let us say you are generating 1000 random numbers. You can do so. So want to generate between 0 to 10. So now what is the range? The range is, earlier it was 0 to 1. So now it is from 0 to 10. So what can I do is I can just multiply 10. That's all. So you can see the, see, this is 0 to 10 uniformly distributed. Suppose somebody asks you to generate random numbers between -1 to +1, uniformly distributed random number -1 to +1. First of all, the range was 0 to 1. So now the range is from -1 to +1. So that is 2. So therefore, the first thing you have to do is, so clear all, clear. So then v is equal to, so rand, so you want to make the, first of all, make the range from 0 to 1 to 2. So 2 times. So that gives you a random number between 0 to 2. Then if you subtract -1, that gives you random number between -1 to +1. You can see that histogram. It will come. You will see it will come. So now you know how to generate random numbers between different values. You can see it is between -1 to +1, right? So now actually you are confident and how to generate random numbers uniformly distributed, then normal distributed. Now you may ask questions. Then there are different other methods of other distribution, like Poisson's distributions, log normal distribution. How to generate that? So just remember that by using statistics, you can generate all kinds of random numbers from normal distribution, normally distributed random numbers by writing simple functions. You can also generate all kinds of random numbers from uniformly distributed random numbers. One simple theorem, there is something called central limit theorem. What is central limit theorem? It says that if there are uniformly distributed random numbers or any kind of random numbers, if you take mean of each of the distributions, you will find they will follow something called a normal distribution. So, this is called central limit theorem. So, using various other theorems and lemmas and also using functions, you can generate other kinds of random numbers. You can also get help from statistics, so which is not loaded right now, statistics toolbox, which I will be covering later on. So, you will find that in statistics, you can easily find the different ways to generate random numbers and different kinds of random numbers. Okay. So, let me come to the next, that is called linearly spaced vector. So, write help lin space. If you have any doubt, you can see, you will get the help. Here it says that generates, you can generate any kind of numbers. You can see it is very clearly written here. Suppose I want to generate, let us say x is equal to lin space, linearly spaced vector between 0 to, let us say 2 pi. I want to have 100 points. See what is happening, right? So, x is a vector, it is a column vector. So, if you want to make it x is a row vector, it is a row vector, you can just make it this, it becomes a column vector. So, this is varying from maximum value is 2 pi and minimum value is 0. So, you can plot that, plot x into sin x and sin x, right? Great. So, you got the curve. So, sin x is varying from 0 to, so if you make grid on, you can see it is starting from 0, it is going up to pi. So, there are 100 uniformly distributed points. Suppose I want to have logarithmic spaced points. For example, I want to have something, when you plot frequency response, etc., your numbers vary from 10 to 10,000 or 20,000. So, you take off. So, in that case, you cannot linearly vary because it will generate number of points. So, you have already used log graphs, semi-log graphs. They are actually, one of the axis is logarithmically spaced. So, sometimes you need to generate logarithmically spaced vectors. So, write log space. See what is happening. So, what does it say? It says that it will generate, you can see logarithmic space vector generates between 10 to the power x1 and 10 to the power xt. It will generate 50 points, logarithmically equally spaced points. Okay. So, 10 to the power x1 and 10 to the power x2, just remember. So, if you want to do that, suppose you want to do log space x1 x2 n, it will give you n points from 10 to the power x1 to 10 to the power x2. Okay. For example, let us take y, or let us say f for frequency, log space. So, I will write from 0, 0 will start means 10 to the power 0. So, I will write 10 to the power 4, I will write 100 points, see what is happening. So, I have given a transpose, so it gives you row vector. So, now you see, if you plot, let us say f, see whether it is logarithmically spaced or not, you can see it is. So, I will plot like this, I will make a bar plot. You can see they are logarithmically spaced. So, you just write grid on. So, these points, so you can see the tip of these points are growing exponentially, that means the points are logarithmically spaced. So, the moment I write log 10 f, let us see what is happening. So, log 10 means it is again uniform, as you can see, or if I write just plot log 10 f. So, what does it mean? It tells you that the frequency is varying uniformly, but logarithmically uniformly. So, if you just plot f, so this is your f in the, this is actually the number of frequencies, and this is the frequency value which is increasing exponentially. Actually, then if you plot log 10 f, so that becomes uniform. So, therefore, they are called logarithmically placed points. If you can see, if you write more on, you will understand more about it. Just write f, you can see. So if you write f1 to 5, you can see 1, 1.0975, 1.2, 1.3. So if you write 1 to 8, see what is happening. So it is blowing off. Then 1 to 9, it is blowing off. You can see 10, it's blowing off. You can see that. That's how it is doing, is it not? So then if you write 20 to 30, let us see what is happening. See 5, 6, 7, 7, it is blowing off actually. So this is called logarithmically spacing. Okay. Write 40 to 50, see it is growing. If you write 10,000, if you write f90 to 10,000, you can see this is logarithmically blowing up. So this is called logarithmically spaced points. Then I said I will tell you something about mesh grid. Here I am going to introduce about some 3D graphs. It will be quite interesting, and there I will tell you the concept of mesh grid. Now let me open an M file. As I have said earlier that I can always write things, all the functions whatever I wrote in the command prompt, I can write in a MATLAB script file, that is .m file. Right now I am opening a .m file, right. So you can see that is taking time. Let me do something else right here. So okay, so in the mesh grid, what I am going to do is I am going to actually plot a function. So let us say my function looks like this. So there is a function called two-dimensional sinc function, where if there are dimensions x and y, and we want to find out z as a function of x and y. So I write z is equal to sine r by r, where r is equal to x square plus y square root over. So it is like this. So there are two dimensions. Here it is x and here it is y. Let us say this is x and y. This is a third dimension z. So I am trying to find out the distance r, which is x square plus y square root over. So all around the distance will be there. So at every point, so I shall find out this function, and this is called sinc function. Sinc function. So this is called sinc function. This is actually sine theta by theta in one dimension. So in one dimension, this function looks like, how does it look like? If this is theta, this is sine theta by theta. So this looks like, at theta is equal to 0, this is 1. So this looks like this. So this is a very nice function in signal processing called sinc function. Okay. This is a sinc function, and the inverse of, if this function is given in frequency domain, this is very interesting. Why it is interesting, I will tell you. I will tell you why it is interesting. That means in frequency domain, if we have a function like this, this is omega, this is sine omega by omega. So if you take the Fourier inverse, just I am telling, don't be worried about it, I shall get back to it. So in the time domain, this turns out to be a function like this. Okay. So Fourier inverse of this becomes a rectangular pulse. So this is very important in signal processing. Anyway, so the two-dimensional sinc function will be important in two-dimensional signal processing or image processing. So my function is sinc. So that is z is equal to sine r by r, where r is equal to x square plus y square root over. Let me say that my x varies from minus, let us say, 6 pi to plus 6 pi. Same thing is y, minus 6 pi to plus 6 pi, let us say. And in the whole region, that is, this is x and y, let us say. So this varies minus 6 pi to plus 6 pi, x varies from minus 6 pi to plus 6 pi. So in this whole region, I am going to evaluate the values of r and then find z. Then I will plot. I will make a plot of x, y, and z. Let us see what is happening and why I need mesh grid at that particular point. Pretty interesting. So let me go back to the editor. This editor is open now. So as usual, I will write clear all to just clear all the variables which is there, which might disturb my programming. Then CLC for screen. So I will write some lecture 1 or lecture 2, something like that, some file name I will give, right. So let me give some file name. So LRN4, let us say, fine. So I will give this file name. So now x varies from, as I said, I will do linspace as usual, linspace minus 6 into pi, okay, to 6 into pi. So how many points I will take? Let me take 100 points only. Similarly, y is equal to x, as simple like that. So now the point is, I want to evaluate z. So for evaluating z, I have to evaluate z for each pair of x and y. So what should I do normally? Under normal circumstances, I shall resort to this. For k is equal to, or k1 is equal to 1 to, see how I am writing, length of x, right. Then for k2 is equal to 1 to length of y, right. Fantastic. So I will write r is equal to r k1 k2 is equal to x k1 square plus y k1 dot k2. Dot is not required, but if you write it also there is no harm. You will know later on that you need to put dots sometimes in functions. Then I will write z is equal to sin r divided by r. Fine, this looks good, is it not? So this looks good. So this is giving me r as a matrix. So r is the point. At each point of x and y, I am having r point, and z I am writing z k1 k2. So that means in each point of the grid, so if you look at it here, so my x is varying from minus 6 pi to plus 6 pi, and y is varying from again minus 6 pi to plus 6 pi. So I am making a grid, you can see. So I am making a grid of how many points? I am making a grid of 100 points. So like this, 100 points in y, then 100 points in x. So these are 100 points in x. So at each point in the grid, all these points, 100 by 100 points, I am going to evaluate the value of r as well as z, right. If I evaluate the value of r and z, so I am able to evaluate z in the whole surface, you know. So now let me do it. So save it first, it's taking a little time. Saved it. So now, so I will write a command like mesh. Mesh is something, you know, mesh means making mesh, connecting in mesh. Mesh is just connecting by wires, okay, connecting by networks. So mesh x, y, and z. Let me see what is the outcome of this. You have to wait a little bit because this computer is a little slow. Next class I will make it all right. So please wait for some time. Let me execute it. Yeah, it has, see, fantastic. So this is your x, this is your y, and this is your z. What? Wow, this is fantastic car. Surface you can see. It's called a sink surface. When you drop, you know how this is very natural. If you really, if you are if you really see, if I write this as, you see, if I write as 1 minus sink, you will find how beautiful again it will be. I just write 1 minus sink. You will see what happens. So here that means it is just 1 minus sink. Whenever you drop, if you drop, you know, a stone in the middle of a pond, you see this kind of wave is created, right. So this is a very beautiful function in two-dimensional imaging. Anyway, So this is the sync function which I plotted. So now I have not used mesh grid anywhere. So what I am trying to do is I am writing a for loop. In the for loop, I am evaluating the value of r, x everywhere. Is it not? So instead of doing all these things, what I can do, I'll just comment all these things. Let me comment. Instead of doing all these things, what I am going to do is I will just define two variables, x and y. See what I am doing. I will write mesh is equal to mesh grid x comma y. What does it do? You must have intuitively thought what it is exactly doing. So it is actually creating two matrices x and y. So each column of x is a copy of the vector x, or each row of x is a copy of the vector. So let me write a column vector. So you will find each column of x is a copy of vector x. So each column of y is a copy of vector y. So that means that if you take any element of x and corresponding element of y and pair it, that will generate a point in the whole surface. So that means x is the x coordinate of all the points on the grid, and x is the matrix of x coordinates, and y is the matrix of y coordinates. Okay. So x is the matrix of x coordinates, y coordinates. So if you write x and y, this gives you all the coordinates pair wise. If you pair all of them, so all the coordinates. That means, so you have created the grid by using mesh grid. Now what I will do is I will write capital R. Capital R, I will write sqrt x dot square. That means individual element wise square, not matrix multiplication. Then y dot square, right? Fantastic. R is equal to this. Then I will write z is equal to sine r by r. It will also give you the same thing, right? So if you execute this, it's doing it, right? So this is how, what is the use of mesh grid. You can look at this program, that will make you more comfortable. It's the same thing. I can see you got the figure, right? So this is the use of mesh grid. That means creating grid. Suppose why you want that it should vary between only minus 2 pi, okay, to plus 2 pi, and I will have only 40 points out there. Fine, no problem. There will be absolutely no problem. You just execute it, see what is happening. So y is constricted. You can see this is y, but x is having 6 pi. So 6 into 3, 18, around 20, minus 20 plus 20. So this is the utility of mesh grid. That is very good, is it not? So now you have understood what is mesh grid. So what are our important commands? Once again, you please see them. So you have already done all the commands. So that means in the help, if you go to the help, you can see that we have already done all the important commands, right? So now let me go to the basic, that is elementary matrices. So then again, let us go to the next, basic array information, right? Then the next is basic array information. Fantastic. So in this, as you can see, size, length, n dimension, number of element, display, is empty, is equal with, equal, nonce, etc. Nonce means not a numbers. So out of them, I find, actually, frankly speaking, I find 2 of them are useful. That is, 3 of them you can say are best: size, length, and display. So only these 3 I consider them to be useful. So size means what? It is the size of the matrix. So see what matrices are there. So let us say size of R. It will tell you 40 by 100. So length of R, can you tell me what it is? So correct, you can, the guess is the maximum, whichever is maximum size, maximum of the size, so it will be 100, right? So length of r dash will be, sorry, so 100. So what is length of x? 100. Length of y also 100, because size of y is, so length and size, these are the, so suppose you want to display r, so you will not require, if you can just type r, you also get this, so they are not very important, right? So let me go to the next, matrix manipulation. So in the matrix manipulation, concatenating arrays, changing the shape and size of the arrays, diagonal, block diagram, extracting the lower triangular part, extracting the upper triangular part, flipped left and right, flip upper and down, okay, flipped dimension. So these things are important. So let me tell you a particular, let me take one particular matrix, let us say rand n. Let me see whether this command is working. Yeah, it is working. So what I am going to do is, I want to display a matrix in the form of an image in the color image. Then I shall apply, okay, I shall apply each of these, okay. So out of them, again I shall tell you what are the important and what are not. So from the matrix manipulation, I can say matrix manipulation, don't think that others are not at all required, they are required, but at the level of programming where you are, even if you are quite advanced, unless you are writing a specific software for commercial use, you don't need many of them. But as you know, you have to learn by yourself. You cannot be taught in one class everything, but I think I can drag you to a sufficient level where you can use your own intelligence to learn many things. So cat is concatenation of arrays. So you can see, just click on this, you see what is help cat. So you can just put arrays size by size, you can see, you can put them together, right? Okay. So it is array or cell, whatever array and cell. I have not told many things about cell. Anyway, so out of them, cat is not at all important, because you can have cat. You know, you can generate matrices, concatenate matrices using simple brackets. Reshape, I think diagonal is one important thing. Block diagonal is another important thing. Triangularization, lower triangular and triangular upper is important. Flip left LR and flip UD are maybe important. Then flip dimension is not important at this moment. Then rotate 90. Then colon, as I said. Then find. Then sub to int and int to sub is not important at the moment. Okay. So into sub is not important at the moment. Then you'll know it in the course of time, okay, when I discuss about other toolboxes. So these are some of the important functions which I am going to discuss right now. Other things, you know, you can discuss on your own, you can find out on your own, okay. So let me take concatenation not by this, by using my own method. Suppose A is a matrix of, let us say I am writing 1 2 3, or I can also write random matrices, ran 2 comma 3. A is a matrix ran 2 comma 3. B is a matrix of 3 comma 4, 3 comma 1, 2 comma 2. Okay. So A is 2 by 3, B is 3 by 2. Okay. So can you concatenate them in any way? Can you put A by the side of B or B? No, it is not possible. But you can do one thing. See, the number of columns of A is matching with the number of rows of B. So I can write a matrix C which taking A and B dash, right? If I write A and B dash, I'll write more of better. So you can see A and B dash, they are now put side by side. Similarly, I can write another matrix D which is B and A dash. Possible? Possible. So you can see A is this, B is this. I can also write a matrix E which is A, okay, just below that B dash. See, so A is becoming just coming. So by semicolon I am putting it by the side. Similarly, I can write also A B dash. So one is adding down, one is adding just in the side. So concatenation is possible just like that. So you don't have to worry about writing this cat command, but you can do it. But in cat command, you can see what is help cat command. You can know more about it. If you see, you can see it is doing the same thing basically. Okay, so it is doing concatenation, right? Okay. Now I shall find out the diagonal. Suppose there is a matrix CLC, clear all. Suppose there is a matrix A which is equal to ran n4. So I want to extract the diagonal elements of A. So just write diagonal of A. That's it. Suppose I want to construct a diagonal matrix from a particular vector. For example, let us say the vector is 1, 2, 3. I want to construct a diagonal matrix using this element. So I will just write. So diagonal can function can make a diagonal matrix from a vector. So the diagonals will be equal to the vectors, the elements of vector, and it can also extract the diagonals of A. So it can also extract the off diagonals. You can see if you write help diag, you will find what are the other things which you can do with diagonals. Then block diagonal. This block diagonal is again a diagonal matrix whose diagonals are, if you consider the blocks, it will tell you the block of the matrix. For example, A is this. Suppose you write diagonal A. So this gives you this diagonal, right? You can see. So diagonal A 0. So this gives you the main diagonal, right? So diagonal A 1, this gives you this diagonal minus this, this and this. Then diagonal A, this is 0, this one is 0, diagonal 0, 0 diagonal, this is first diagonal, the second diagonal, this is third diagonal, right? 3, it will give you the last element. Suppose you write minus 3, it will give you the lower. So minus 1, it will give you the lower diagonal, right? So these are the use of diagonal matrices. Now suppose I want to construct a block diagonal matrix, taking some elements. This is very much, block diagonal matrix is very much required in matrix manipulation and linear algebra. So you can see, suppose I want to construct a block diagonal. Let us say A is a, I'll just have some random matrices. Let us say rand 2, 3, and B is some rand, let us say rand n 2, like that. So A is a matrix like this, B is a matrix like this. Suppose I will write BLK diagonal, C is block diagonal A comma B. See what is happening. So A will come in one diagonal first, then B will come, you can see. So this matrix is A, then it is filled with zeros, then this is B, this is filled with zeros. So this is the matrix whose block diagonal elements are matrix A and matrix B, right? Is that clear? So this is block diagonal. Then lower triangular matrix, upper triangular matrix. So this is your A. Suppose I write try upper A. What do you get? You will get the upper triangular matrix. From this, actually you will get this diagonal will be gone, this diagonal will be there, you will get the upper triangular. Suppose I write lower triangular, so you can find this is the lower triangular matrix. Suppose A is a square matrix, let us say A is a square matrix having 4 by 4 structure. Suppose I write try L A, what are you going to get? So try A will keep the diagonal, you can see it is keeping all the diagonal, keep the elements below the diagonal and fill the upper elements with 0, 0. Similarly, if I make it try UA, it will give you the upper triangular matrix, as you can see here. It will keep the diagonal, and upper triangular it will extract, then the lower triangular will become 0. So these are useful in matrix manipulations when you do Gaussian elimination, singular value decomposition, QR decomposition, etc. So then there are some few things like flip LR, flip UD, and rotate 90. Let us see what is flip LR. So if you are looking at an image from the front, if you just flip the image, how it will see, how you will see. So that is like flip LR or flip UD. So let us see CLC, clear all. So now let me have a matrix A which is equal to and n, let us say 10 by 10 matrix. I will do little manipulation, some cube I will do, fine. So that means if I do image scale, I will do scale, for example, because the value should be image scale. It is called image SC, means you will know more about it later on. Scale, scaled image of A. See what is happening. So this is the scaled image of A. You can see here. You can see this is red, this is red, this is yellow. You know, suppose, so then what I will do is, look, I will do flip LR A. Let us see what is happening. I will do it in a different figure. Figure 2 means it will take another figure, right? So this is your flip LR. That means the left has become right. So this is one image. So this is the mirror image, you can see. So this was here, now this is here. This was here, now this is here. Correct? So this was here, now it has just flipped, right? So this whole thing is coming here. Then I will take flip UD, let us say. So it will flip around the horizontal axis. You can see this is figure 3. So figure 1, with respect to figure 1, if you see, it is having flipping in the UD horizontal axis. You can see. So it was here, now it is here. Okay, so this was here, now it is here, or it was here, now it is here. So this is just flipping around the horizontal axis. Similarly, suppose I will take another figure. I will have rotate 90. So I will see with respect to figure 1. So this is my figure 1. This is rotate 90. You can see this. The whole thing has been rotated. You can see in the anti-clockwise fashion. You can see that. This is your figure 4. This is figure. So this thing has come here, as you can see. This thing comes here. This thing goes here. This thing comes here. This is rotated, as if the figure has been rotated. So you can see. So these are some of the functions, and find is pretty easy. So I will just write close all. You will see all the windows will close. Right. So now I will write find. What is find? So find means find what are the elements which are non-zero, right? Okay. So now suppose I will write X is equal to identity matrix 4. So now I find X. So what elements you are going to get? So we are going to get. So X will become a vector first. Okay. So that means V is X colon. So this is your V. So then it is finding X is same as finding V, right? So first element, sixth element, 11th element, all are becoming 0. So this is your finding, right? You can see this linear array X that are non-zero. X may be logical expression, whatever. So right. So this is what you have learned in this class. So then a few more things. Multi-dimensional array, permutation. You need only permutation sometimes. ND grid, etc. That is just like mesh grid, but it in n dimension. Then permutation and inverse permutation you may need. Circular shift is important here. So I will be discussing circular shift permutation in next class. In the next class, the main thing which I am going to discuss is these things actually are important, but I will just tell you next class. So next class I will continue with these special matrices. So after I complete these special matrices, which will be I will tell you about briefly about these matrices and their origin. Then I shall switch to what I have promised is solution of differential equation and curve fitting. So thank you very much.